Hi, I'm Lauren, and today I'll be presenting my lab report for Physics 2211. For this particular experiment, I previously investigated the motion of a mass oscillating vertically on a spring from pre-lecture videos. Similar to that video, I examined the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. While this particular motion seems to be complicated, we can understand and even predict this motion using the same techniques and fundamental principles explored before. I chose option 1, which involved performing a video analysis only. To do this, I used Tracker to extract the position data for the mass in the video shown. After putting the video in Tracker, I was able to plot the mass's position in both the x and y directions at different time intervals, creating graphs of the motions of the mass. Then I copied only the x and y position data into a Google spreadsheet for later. Starting with the starter code, I began to tweak the necessary data needed for the prediction model for the motion of the mass. For the motion of the mass, using option 1, we were given most of the information to put in the code, such as mass, initial velocity, initial time, initial position, L and L naught. For the initial conditions, I made the mass equal to 0.402 kilograms, the ball position equal to negative 6.950, and the ball's velocity 0, 0, 0. Next, I needed to complete the rest of the necessary data using my knowledge of common formulas. So the spring stiffness was given. It was 6.83. L naught was negative 0.123. L was the ball's position minus the spring's position. L hat is L divided by the magnitude of L. And S is equal to the magnitude of L minus L naught. Most of those were given. Some were the previously known formulas. Then I had to calculate all of the needed energies. So K is equal to 1/2 times the ball's mass times the magnitude of the ball's velocity squared. The potential gravitational is the ball's mass times G times the ball's position in the y direction. And the spring potential is 1/2 spring stiffness times S squared, bringing the total energy equal to K plus UG plus US. The rest of the code was simply using more known formulas and using the previous data to evaluate them, including gravitational force, spring force, and net force, then using the momentum principles for position and velocity to update the spring, and finally calculate energy changes. The purpose of this lab was to compare the predicted motion and observed motion of the mass in both the x and y directions, and then plot the energy changes that were computed in the model, which is the change in kinetic, gravitational potential, spring, and total energies. Possible room for error results from my own collected data within Tracker. If you take a look at my graphical models, the experimental data is oscillating by only a very small amount, whereas it should be oscillating about the same as the computational model predicted. So what does this mean? For the model system, is the energy principle satisfied? Yes, the energy principle is satisfied. I know this because within my model, I accounted for every force acting on the mass, spring, and gravitational, and then pretty much calculated the work for each one around the corresponding displacement. That is the energy principle itself. Finding the total energy for the system required calculating the work for each force, then adding them all together, assuming that there's no heat exchange between the systems. Now, if my graphs were pictured correctly, then this would also be supported graphically. Estimate the period of oscillation from the x position data and the y position data. The period of oscillation in the x position is estimated to be around 1.524 seconds, and the period of oscillation for the y position is estimated to be about the same. The formula for the period of oscillation is 2 pi times the square root of m over k. So in both the x and y positions, the mass nor the spring constant changed. Therefore, the period of oscillation for both is the same after plugging in the given information into the formula. Thank you.